Calculating reaction rates. The rate of a reaction tells you how much product forms or how much reactant is used up over a specific period of time. You calculate it using a simple formula. Rate equals the amount of reactant used or product formed divided by time. On a graph, the rate at any specific point is found by calculating the gradient of a tangent down to the curve. A steeper slope indicates a faster rate. As the reactants get used up, the reaction slows down, causing the curve to flatten out over time. In the exam, if they give you a curve on a graph, always draw a clear straight tangent line against the curve and calculate its gradient, which is change in y divided by change in x. Remember to show your working and state your units, which are usually centimeters cubed per second for gases or grams per second for mass. Remember, rate is just speed. A steeper slope means a faster reaction. Chemical reactions can only happen when reacting particles collide with each other with enough energy. This minimum amount of energy required for a reaction to take place is called the activation energy. If particles collide with less energy than this, they simply bounce off one another unchanged. Therefore, to speed up a reaction, you must increase the frequency of successful collisions. In the exam, when you're asked to explain why a factor speeds up a reaction, always phrase your answer using collision theory. State that the factor increases the frequency of collisions, which leads to a greater number of successful collisions per second. So what are the factors affecting rate? There are four main factors that speed up a chemical reaction. Increasing the temperature gives particles more kinetic energy, making them move faster. This means they collide more frequently, and a higher proportion of those collisions have enough energy greater than the activation energy. Increasing the concentration of a solution, or the pressure of a gas, means there are more particles packed into the same volume, which increases the frequency of collisions. For solids, breaking them up increases the surface area, exposing more particles to react at once. Adding a catalyst changes the reaction route entirely. Catalysts and activation energy. A catalyst is a substance that speeds up the rate of a chemical reaction but remains chemically unchanged at the end, meaning it's not used up. It works by providing an alternative reaction pathway that has a lower activation energy. This allows a much higher proportion of the colliding particles to have enough energy to react successfully. Because the catalyst is not used up in the process, you only need a small amount of it, and it can be used over and over again. Required practical, rates of reaction. The classic rates required practical involves reacting sodium thiosulfate with hydrochloric acid. As these two clear solutions react, they produce a fine yellow precipitate of sulfur, which gradually turns the solution cloudy. To measure the rate, you place the reaction flask over a piece of paper marked with a black cross and time how long it takes for the cross to completely disappear. A shorter time means a faster reaction rate. You repeat this process while changing the concentration of the sodium thiosulfate to investigate its effect. In the exam, you're often asked to identify the variables in this experiment. The independent variable is what you deliberately change. That's the concentration of sodium thiosulfate. The dependent variable is what you measure, which is the time taken for the cross to disappear. The control variables that you must keep constant include the total volume of the liquid, the temperature, and the depth of the liquid. Reversible reactions. Some chemical reactions can go both ways. A reversible reaction is always represented in a chemical equation by a double-headed arrow. In the forward direction, reactants turn into products. In the reverse direction, those products break back down into the original reactants. A classic example is ammonium chloride. Heating it causes it to decompose into ammonia and hydrogen chloride gases, but cooling those gases back down causes them to recombine into solid ammonium chloride. In the exam, always look out for the double arrow symbol. Remember that energy changes are also perfectly reversible. If a reaction is exothermic in the forward direction, it will be endothermic in the reverse direction by the exact same amount of energy. Dynamic equilibrium. When a reversible reaction happens inside a closed system, where no reactants or products can escape, it eventually reaches a state called dynamic equilibrium. This doesn't mean the chemical reaction has stopped. Instead, it means the forward and reverse reactions are occurring at the exact same rate. Because these two speeds are perfectly balanced, the overall concentrations of all the reactants and products remain completely constant. In the exam, the absolute keyword here is dynamic. If an examiner asks you to define equilibrium, your answer must include two specific points. The rate of the forward reaction equals the rate of the reverse reaction, and the concentrations of reactants and products remain constant. Crude oil and hydrocarbons. Crude oil is a complex mixture of a vast number of compounds called hydrocarbons are molecules made of hydrogen and carbon atoms only. Crude oil was formed millions of years ago from the remains of ancient biomass, mainly plankton, that settled at the bottom of oceans, where it was buried under mud and subjected to intense heat and pressure over millions of years. It's a finite resource, meaning it's being consumed much faster than it can actually form, and it will eventually run out. In the exam, because crude oil is a mixture and not a pure substance, it does not have a single sharp boiling point. Instead, it boils gradually over a wide range of temperatures as the different chain lengths separate. So crude oil is just nature's massive collection of carbon chains all tangled up together. Alkanes. Alkanes are described as saturated hydrocarbons. The term saturated means that all the carbon atoms are joined together by single covalent bonds, meaning the molecule contains the maximum possible number of hydrogen atoms. The first four alkanes you need to know are methane, 1 carbon, ethane, 2 carbons, propane, 3 carbons, and butane, 4 carbons. They follow the general mathematical formula CnH2n plus 2. As the carbon chain gets longer, the boiling point increases. The liquid becomes thicker and more viscous. It becomes less flammable and it turns darker in colour. In the exam, you must memorize the names and formulae of the first four alkanes: methane, CH4, ethane, C2H6, propane, C3H8, and butane, C4H10. Be prepared to draw their displayed formulae showing every single atom and bond line clearly. Remember the acronym MEPB? Monsters eat pupils' brains: methane, ethane, propane, butane. Short-chain hydrocarbons are highly useful because they ignite easily and flow smoothly compared to the thick, long-chain hydrocarbons. Fractional distillation. This is how we separate crude oil into its different sections. The crude oil is heated until it evaporates. Then it's fed into a tall tower called a fractionating column. The column is hot at the bottom and cool at the top. As the vapours rise, they cool down. The long-chain hydrocarbons have high boiling points, so they condense and are collected near the bottom. The short-chain hydrocarbons have low boiling points, so they rise higher up before condensing and are collected near the top. Each collected part is called a fraction, and each fraction contains molecules with a similar number of carbon atoms. In the exam, the key idea is that hydrocarbons are separated by their boiling points, and boiling point depends on the length of the carbon chain. Useful fractions include petrol, kerosene for jet fuel, diesel, and bitumen for road surfaces. When any hydrocarbon is burned with an abundant supply of oxygen, it undergoes complete combustion. The carbon and hydrogen are fully oxidized, meaning the only two products formed are carbon dioxide and water. However, if oxygen is limited, incomplete combustion occurs. This produces toxic carbon monoxide gas, along with unburnt carbon particles released as black soot. In the exam, carbon monoxide is dangerous because it's a toxic, colourless and odourless gas. It binds irreversibly to the hemoglobin in your red blood cells, preventing them from carrying oxygen around the body. Remember the standard word equation: hydrocarbon plus oxygen gives you carbon dioxide plus water. Cracking. Industrial oil refining produces too many long-chain hydrocarbons from crude oil, which are thick and not in high demand. Conversely, there's a massive shortage of short-chain hydrocarbons, like petrol, which are highly sought after. Cracking is a thermal decomposition process used to break these long, less useful molecules down into smaller, more valuable ones. There are two main types: catalytic cracking, which uses a hot catalyst at lower temperatures, and steam cracking, which mixes the hydrocarbons with steam at very high temperatures. Cracking always yields a shorter alkane and at least one alkene, which is a type of unsaturated hydrocarbon used to manufacture plastics and polymers. In the exam, always specify that cracking requires high heat and either a catalyst or high pressure. Importantly, always mention that the process creates alkenes, which are far more reactive than alkanes and turn bromine water from orange to colourless. So cracking simply cracks the long, useless carbon chains in half, much like snapping a long stick into smaller, more useful pieces. Pure substances and formulations. In chemistry, a pure substance consists of only a single element or a single compound that's not mixed with any other substance. Pure substances can be easily identified because they melt and boil at precise specific temperatures. In contrast, a mixture does not have a sharp melting point. It will melt or boil gradually over a wide range of temperatures. A formulation is a very specific type of mixture that's been carefully designed as a useful product. In a formulation, every single ingredient is measured out precisely to ensure the product has the exact properties required. Examples include paints, medicines, alloys, and fertilisers. In the exam, a pure substance melts and boils at one fixed temperature. A mixture melts and boils over a range. This is the simplest way to tell them apart from a data table. So a formulation is a recipe. Every ingredient is measured out on purpose to get the exact result that you want. Chromatography. Paper chromatography is a method used to separate a mixture of soluble coloured substances, such as the different dyes in an ink. You draw a starting line in pencil near the bottom of the paper, place a spot of the mixture on it, and dip the bottom of the paper into a solvent. The solvent travels up the paper, carrying the different substances with it. Substances that are more attracted to the solvent travel further up, while substances more attracted to the paper travel less far. So the mixture separates out into individual spots. In the exam, always draw the starting line in pencil, never pen. Pencil is insoluble, so it will not run up the paper and ruin the result. A pure substance produces only one single spot, whereas a mixture separates into 2 or more spots. RF values and required practical. Chromatography. Each substance can be identified by its RF value. The RF value is calculated using the formula RF equals the distance moved by the substance divided by the distance moved by the solvent. Because it's one distance divided by another, an RF value is always a number between 0 and 1, and it has no units. In the required practical, you separate the colours in food dyes or inks, measure both distances carefully with a ruler from the pencil line, and calculate the RF value for each spot. In the exam, always measure to the centre of each spot, and always measure both distances from the same pencil starting line. The same substance will always give the same RF value in the same solvent, which is how you identify it. Testing for gases. There are 4 common gas tests that you must know. To test for hydrogen, you hold a lit splint at the mouth of a test tube. Hydrogen burns with a squeaky pop. To test for oxygen, you place a glowing splint into the tube, and oxygen relights the glowing splint. To test for carbon dioxide, you bubble the gas through lime water. Carbon dioxide turns the lime water cloudy or milky. To test for chlorine, you hold damp blue litmus paper in the gas. Chlorine bleaches the litmus paper white. It might turn red first because chlorine is acidic. In the exam, learn these word for word, including the result. Squeaky pop for hydrogen, relights a glowing splint for oxygen, turns lime water cloudy for carbon dioxide, and bleaches damp litmus paper for chlorine. The early atmosphere. The Earth is around 4.6 billion years old, and for the first billion years it was extremely volcanically active. These volcanoes released huge amounts of gas, so scientists believe the early atmosphere was mostly carbon dioxide, with very little or no oxygen, rather like the atmospheres of Mars and Venus today. The volcanoes also released water vapour and small amounts of other gases like nitrogen, methane and ammonia. As the Earth cooled, the water vapour condensed to form the oceans. In the exam, be careful with the wording. We can't be completely certain about the early atmosphere because it was so long ago and there's limited evidence, so scientists use theories and models. The 2 big points are mostly carbon dioxide and little to no oxygen. How the atmosphere changed. 2 main changes turned that early atmosphere into the one that we breathe today. First, oxygen increased. About 2.7 billion years ago, algae and then plants evolved and began photosynthesis, taking in carbon dioxide and releasing oxygen. Over billions of years, this slowly built up enough oxygen for animals to evolve. Second, carbon dioxide decreased. A lot of it dissolved into the newly formed oceans, where it formed carbonate sediments and rocks. Carbon was also locked away inside the bodies of plants and animals, which over millions of years became fossil fuels such as coal, oil and gas. In the exam, link oxygen rising directly to photosynthesis by algae and plants. Link carbon dioxide falling to it dissolving in oceans, forming sedimentary rocks and being trapped in fossil fuels. Greenhouse gases and climate change. Some gases in the atmosphere are called greenhouse gases because they trap heat and keep the planet warm enough for life. The main ones are carbon dioxide, methane and water vapour. They work by letting short wavelength energy from the sun pass through to warm the Earth. They also absorb the longer wavelength heat radiation that the Earth gives off and re-radiate some of it back down. Human activities are increasing the amounts of carbon dioxide. from burning fossil fuels and deforestation, and methane from farming livestock and landfill sites. This extra greenhouse gas is causing global climate change. In the exam, the consequences to learn include rising global temperatures, melting ice caps and polar ice, rising sea levels and flooding, more extreme weather, and changes to the distribution of wildlife. Always link human activity to the increase in greenhouse gases. Think of it like the greenhouse gases are a duvet around the Earth, and a thicker duvet traps more heat. Carbon footprint. The carbon footprint is the total amount of greenhouse gases, so carbon dioxide and methane, given off over the full life cycle of a product, service, or event. To slow down climate change, we need to reduce these footprints. We can do this by using renewable energy sources instead of fossil fuels, by being more energy efficient, by capturing and storing carbon dioxide before it reaches the atmosphere, and through government actions like taxes or carbon caps on businesses. In the exam, you might be asked why it's difficult to reduce carbon footprints. Good reasons include the high cost, a lack of public willingness to change habits, incomplete scientific information, and the difficulty of making international agreements between countries. Atmospheric pollutants. Burning fuels releases several harmful pollutants into the air. Incomplete combustion produces carbon monoxide, which is a toxic, colourless, odourless gas, and soot, which we also call carbon particulates, which causes breathing problems and global dimming. Most fuels contain small amounts of sulphur, which burns to form sulphur dioxide. At the high temperatures inside engines, nitrogen and oxygen from the air react to form oxides of nitrogen. Both sulphur dioxide and oxides of nitrogen dissolve in clouds to cause acid rain, and both also cause respiratory problems in humans. In the exam, match each pollutant to its problem. Carbon monoxide is toxic, particulates cause global dimming and breathing problems, sulphur dioxide and oxides of nitrogen cause acid rain and respiratory issues. Using the Earth's resources. The Earth provides us with everything we need for warmth, shelter, food, and transport. These resources are split into two types. Finite resources, like fossil fuels and metal ores, are being used up far faster than they can be replaced, so they will eventually run out. Renewable resources, like timber and fresh water, can be replaced as quickly as we use them. Sustainable development means meeting the needs of people today without damaging the ability of future generations to meet their own needs. In the exam, chemistry helps sustainability in many ways, improving farming and agriculture and developing new materials, as well as finding ways to reuse and recycle limited resources. Know the difference between finite and renewable clearly. Potable water. Potable water means water that's safe to drink. Importantly, potable water is not the same as pure water because it still contains low levels of dissolved salts and some microbes. In the UK, we make potable water from fresh water by choosing a suitable source such as a reservoir, river, or aquifer, then passing it through filter beds to remove solids, and finally, sterilising it to kill microbes. Sterilising can be done with chlorine, ozone, or ultraviolet light. In very dry countries with little fresh water, seawater must be desalinated by distillation or reverse osmosis, but this uses large amounts of energy. In the exam, remember the two clear steps for fresh water: filtration to remove solids, then sterilisation to kill microbes. Desalination is only used when there's not enough fresh water because it's expensive and energy hungry. Required practical analysis and purification of water. In this required practical, you analyse water samples and then purify one by distillation. First, you test the pH of each sample using a pH meter or universal indicator. Then you find out how much dissolved solid is present by evaporating a measured volume of the water and weighing what's left behind. Finally, you purify the water using distillation. You boil the water so it evaporates. Then you cool the steam so it condenses back into a separate clean container, leaving the dissolved solids behind. In the exam, remember that distillation works because the dissolved solids have very high boiling points, so they stay behind in the flask while the pure water evaporates and is collected. The distilled water should have a neutral pH of 7 and leave no solid when evaporated. Wastewater treatment. Large amounts of wastewater are produced by homes, sewage, agriculture, and industry, and this must be treated before it safely returns to the environment. The treatment happens in stages. First, screening removes large solids and grit. Next, sedimentation lets the waste settle in a large tank, separating into a liquid called effluent on top and a solid sludge at the bottom. The sludge is then broken down by anaerobic digestion, so that's without oxygen, which also produces useful biogas. The effluent is treated by aerobic biological treatment, where bacteria use oxygen to break down the remaining organic matter and harmful microbes. In the exam, learn the order: screening, then sedimentation, then anaerobic digestion of the sludge, and aerobic treatment of the effluent. Note that treating sewage needs less energy than desalinating seawater, which is a common comparison question. Life cycle assessments. A life cycle assessment, or LCA, is carried out to work out the total environmental impact of a product across its entire life. It looks at 4 main stages: getting the raw materials, manufacturing the product, using the product, and finally disposing of it at the end of its life. At each stage, the LCA considers things like the use of resources, the energy needed, and any pollutants released to the water, land, or air. In the exam, be ready to explain why LCAs are not fully objective. Measuring the effect of pollutants involves making value judgments, so the results can be biased. For example, a company might design an LCA to make its own product look better. Energy and material can be used fairly accurately, but the impact of pollution is harder to judge. Reduce, reuse, recycle. The simplest way to make resources last longer and reduce environmental damage is to use less of them in the first place. The 3 R's put this in order. Reducing means using smaller quantities of raw materials and energy. Reusing means using an item again for the same or a new purpose, like refilling a glass bottle. Recycling means processing used materials, such as melting down metals or glass, so that they can be used in new products. Recycling metals in particular saves a huge amount of energy and ore compared with extracting fresh metal from the ground. In the exam, the order of preference is reduce first, then reuse, then recycle. A strong point to make is that recycling uses much less energy and conserves limited resources compared with mining and extracting new raw materials. The Chatelier's principle. On the higher paper, you need to predict what happens to a reversible reaction at equilibrium when you change its conditions. The rule that lets you do this is called Le Chatelier's principle. It states that if you change the conditions of a system at equilibrium, the position of that equilibrium will shift to oppose or counteract the change you made. In other words, the system always tries to cancel out whatever you do to it. The three conditions you can change are concentration, temperature, and pressure. In the exam, the position of equilibrium tells you whether there's more product or more reactant in the mixture. Shifts to the right means more product forms. Shifts to the left means more reactant forms. Changing concentration. If you increase the concentration of a reactant, the equilibrium shifts to the right to use it up, so more product is made. If instead you remove or decrease the concentration of a product, the equilibrium also shifts to the right to replace it, again making more product. The system always moves in the direction that opposes your change, either using up what you added or making more of what you took away. In the exam, a common application, in industry, products are often removed as soon as they form. This keeps shifting the equilibrium to the right and increases the yield. Always state which side now has more substance and why. Change in temperature. Temperature changes depend on whether the forward reaction is exothermic, gives out heat, or endothermic, takes in heat. If you increase the temperature, the equilibrium shifts in the endothermic direction to absorb the extra heat. If you decrease the temperature, the equilibrium shifts to the exothermic direction to release more heat. So, for an exothermic forward reaction, raising the temperature actually shifts the equilibrium backwards and reduces the yield of product. In the exam, first identify which direction is exothermic and which is endothermic. The question will tell you. Then apply the rule. Heat up favours endothermic, cool down favours exothermic. Always link the shift back to the yield of product. Change in pressure. Pressure only affects reactions involving gases, and it depends on the number of gas molecules on each side of the equation. If you increase the pressure, the equilibrium shifts towards the side with the fewer molecules of gas. This is because that reduces the pressure again. If we decrease the pressure, the equilibrium shifts towards the side with the greater number of gas molecules. To answer these questions, you must count the number of gas moles on each side using the big numbers in the balanced equation. In the exam, always count the moles of gas on each side first. Increase pressure, then the equilibrium goes to the side with the fewer gas molecules. If both sides have the same number of gas molecules, changing the pressure has no effect on the position of equilibrium. These slides cover the extra triple only content, the separate chemistry GCSE. They add a much larger organic chemistry section, far more chemical analysis tests, and extra topics in using resources. Slides marked HT are higher tier within triple. Reactions of alkenes. Alkenes are unsaturated hydrocarbons that contain a carbon-carbon double bond, which makes them more reactive than alkanes. You need to know 4 reactions. With hydrogen, using a nickel catalyst, an alkene gains hydrogen across the double bond to form an alkane, and this is called hydrogenation. With steam, water, using a catalyst, an alkene forms an alcohol. This is how ethanol is made industrially. With the halogens, such as bromine, an alkene reacts to form a dihalogen compound, and this is the basis of the bromine water test. In all these reactions, the double bond opens up and atoms add across it, which is why they are called addition reactions. In the exam, the bromine water test distinguishes alkenes from alkanes. An alkene decolorizes orange bromine water, turning it colourless because of an addition reaction, while an alkane leaves it orange. Think of it like this: the double bond is an open door, atoms walk in and add on. Every alkene reaction is an addition. Alcohols. Alcohols are a family, or homologous series, with a functional group, OH. The first four are methanol, ethanol, propanol, and butanol. They share key properties. They dissolve in water to form a neutral solution. They react with sodium to produce hydrogen. They burn in air or combust, and they are oxidized by microbes or oxidizing agents to form carboxylic acids, which is why wine left open turns sour as it turns into vinegar. Alcohols are widely used as fuels and as solvents. Ethanol can be produced industrially by hydration of ethene or by fermentation of sugars using yeast at around 30 degrees Celsius in anaerobic conditions. In the exam for fermentation, learn the conditions. Yeast, a warm temperature, about 30 degrees Celsius, and no oxygen, anaerobic. The products are ethanol and carbon dioxide. Know that the functional group OH is what makes them all alcohols. Carboxylic acids. Carboxylic acids are another homologous series with the functional group COOH. The first four are methanoic, ethanoic, propanoic, and butanoic acid. Ethanoic acid is the acid found in vinegar. They behave like typical acids. They dissolve in water to form acidic solutions, and they react with carbonates to produce carbon dioxide, a salt, and water. They also react with alcohols in the presence of an acid catalyst to produce sweet-smelling compounds called esters. Importantly, carboxylic acids are weak acids. They only partly ionize in water, so they have a higher pH than a strong acid of the same concentration. In the exam, the phrase to use is that weak acids only partially ionize in solution. That's why at the same concentration, a weak carboxylic acid has a higher pH, or is less acid, than a strong acid like hydrochloric acid. Addition polymerisation. Alkenes are very useful because they can join together to make polymers, which are very large molecules. In addition polymerisation, many small alkene molecules, the monomers, add together to form one long polymer chain, and this is the only product. Nothing else is made. For example, many ethene molecules join to form polyethene or polythene. During the reaction, the carbon-carbon double bond in each monomer opens up so it can bond to the next monomer. In the exam, you must be able to draw the repeating unit. Take the monomer, change the double bond to a single bond, and add a bond extending out of each end through brackets with a small n outside. The polymer is named by putting the monomer name in brackets after poly, e.g. polypropene. Condensation polymerization, and this is for the higher tier. Condensation polymerization involves monomers that have two functional groups, one at each end. A common example uses a diol, which has two OH groups, reacting with a dicarboxylic acid, which has two carboxylic groups, to form a polyester. Each time two monomers join, a small molecule, usually water, is lost. So unlike addition polymerization, there are always two products, the polymer and the small molecule given off. This requires two different monomers, each with two reactive ends. In the exam, the clearest way to tell the two types apart, Addition polymerization has one monomer, an alkene, and one product. Condensation polymerization has monomers with two functional groups and makes two products, the polymer plus a small molecule such as water. Naturally occurring polymers. Nature makes its own polymers. Proteins are polymers made from amino acid monomers joined by condensation polymerization, and different proteins are built from different combinations of amino acids. DNA, which carries our genetic instructions, is a very large molecule made of two polymer chains, made from monomers called nucleotides, and it's twisted into a double helix shape. Starch and cellulose are both natural polymers too, and they're made from the sugar called glucose, which is the monomer, and plants use them for energy storage and structure. In the exam, learn the monomer for each one. Amino acids make proteins, nucleotides make DNA, and glucose, sugar, makes both starch and cellulose. DNA is described as two strands in a double helix. Flame tests. We now add the extra triple analysis tests, starting with identifying metal ions. A flame test identifies some metal ions by the colour they turn a flame. You dip a clean wire loop into the sample and hold it in a blue Bunsen flame. Lithium ions give a crimson or red colour. Sodium ions give a yellow flame. Potassium ions give a lilac flame. Calcium ions give an orange-red flame, and copper ions give a green flame. In the exam, a limitation to remember: if a sample contains a mixture of ions, the colour of one, especially the strong yellow of sodium, can hide the colour of the others. This is why instrumental methods are often more reliable. Metal hydroxide tests. A second way to identify metal ions is to add sodium hydroxide solution and look for a coloured precipitate. That's an insoluble solid. Aluminium, calcium, and magnesium ions all give a white precipitate, but you can tell aluminium apart because its precipitate dissolves again sodium hydroxide, while calciums and magnesiums do not. The transition metals give colours. Copper 2 gives a blue precipitate, iron 2 gives a green precipitate, and iron 3 gives a brown precipitate. In the exam, for the three white precipitates, add excess sodium hydroxide to separate them. Only aluminium hydroxide redissolves. Learn the three coloured ones precisely: copper blue, iron 2 green, and iron 3 brown. Tests for negative ions, anions. You also need 3 tests for negative ions. For carbonate ions, add a dilute acid. If it fizzes and the gas produced turns lime water cloudy, carbonate is present, and the gas is carbon dioxide. For halide ions, chloride, bromide, and iodide, add dilute nitric acid followed by silver nitrate solution. Chloride gives a white precipitate, bromide gives a cream precipitate, and iodide gives a yellow precipitate. For sulfate ions, add dilute hydrochloric acid followed by barium chloride solution, and a white precipitate confirms sulfate is present. In the exam, don't forget the acid step before the main test: nitric acid before silver nitrate for halides, and hydrochloric acid before barium chloride for sulfates. The acid removes carbonate ions, which would otherwise give a false result. Required practical: identifying ions. In this required practical, you use the tests we've just covered to identify the ions in unknown salts. You carry out flame tests and sodium hydroxide tests to find the positive metal ions, cations, and you use the acid, silver nitrate, and barium chloride tests to find the negative ions, anions. By combining the results, you can name the full compound. For example, a green flame plus a white precipitate with barium chloride will point to copper sulfate. In the exam, work systematically. Identify the cation and the anion separately. Then put them together to name the salt. Always note the safety point that several of these reagents are irritants or harmful, so eye protection is very necessary. Instrumental methods and flame emission spectroscopy. Modern laboratories often use machines, instrumental methods, instead of chemical tests because they're more accurate. They're also more sensitive because they detect tiny amounts, and they're much faster. One example you must know is flame emission spectroscopy. This is used to identify metal ions in solution. The sample is put into a flame, and the light given off is passed into a spectroscope. This produces a line spectrum that's unique to each metal ion, a bit like a fingerprint. The position of the lines identifies the metal, and the intensity or brightness of the lines shows the concentration. In the exam, give the 3 advantages of instrumental methods clearly. They're more accurate, more sensitive, and faster than the old chemical tests. Flame emission spectroscopy can also analyse mixtures of metal ions, which simple flame tests cannot. Every metal has its own barcode of light. The lines say which metal, the brightness says how much. Corrosion and its prevention. Corrosion is the destruction of materials by chemical reactions with substances in the environment. The rusting of iron is the key example, and it needs both oxygen and water to happen. If either one is missing, iron will not rust. We can prevent corrosion in 2 ways. One is to use a barrier to keep out air and water, such as painting, oiling, greasing, or coating of plastic. The other is sacrificial protection, where a more reactive metal, like zinc or magnesium, is attached to the iron. It corrodes instead of the iron, sacrificing itself to protect it. In the exam, galvanizing is coating iron with zinc. It works as both a barrier and as sacrificial protection. Aluminium does not corrode away like iron because it forms a thin, strong oxide layer that protects the metal underneath. Alloys. Most metals we use every day are actually alloys, mixtures of a metal with one or more other elements. Alloys are usually harder than the pure metal because the different sized atoms distort the regular layer of atoms, making it harder for them to slide over each other. Steel is an alloy of iron with carbon. High carbon steel is hard but brittle, while low carbon steel is softer and easily shaped. Stainless steel contains chromium and nickel to resist corrosion. Bronze is copper with tin, and brass is copper with zinc. Gold used in jewellery is alloyed with metals like silver and copper, and its purity is measured in carats, where 24 carat is pure gold. Aluminium alloys are useful because they have a low density. So in the exam, the reason alloys are harder is worth memorising. The atoms are different sizes, so they distort the layers and stop them sliding. Match each alloy to its components. Steel is iron and carbon, brass is copper and zinc, bronze is copper and tin. Ceramics, polymers and composites. Triple chemistry also looks at how the properties of materials suit their uses. Ceramics include clay pottery, made by shaping wet clay and then firing it hard in a kiln. And glass, soda lime glass, is made by heating sand, sodium carbonate and limestone, while borosilicate glass melts at higher temperatures. Polymers behave in 2 ways. Thermosoftening polymers melt when they're heated because their chains are tangled but they're separate, so they can be remolded, whereas thermosetting polymers have strong crosslinks between chains, so they don't melt. A composite is made of two materials, a reinforcement held together by a binder or a matrix, combining their best properties like fiberglass or carbon fiber. In the exam, the key polymer distinction is crosslinks. Thermosetting polymers have crosslinks and don't melt. Thermosoftening polymers don't have crosslinks, so they do melt and can be reshaped. Choose materials by matching their properties to what the object needs to do. The Haber process. The Haber process makes ammonia, which is essential for fertilisers. It combines nitrogen and hydrogen in a reversible reaction. Nitrogen plus hydrogen are in equilibrium with ammonia. The nitrogen comes from the air and the hydrogen comes mainly from natural gas, methane. The gases are passed over an ion catalyst at a temperature of about 450 degrees Celsius and a high pressure of about 200 atmospheres. Because the reaction is reversible, not all the gases convert. So the ammonia is removed by cooling it to a liquid, and the unreacted nitrogen and hydrogen are recycled back into the reactor. In the exam, learn the conditions precisely. 450 degrees Celsius and about 200 atmospheres, and an ion catalyst. Know the raw materials, nitrogen from the air, and hydrogen from natural gas. Choosing the Haber conditions, and this is higher tier triple. The conditions in the Haber process are a compromise, chosen using Le Chatelier's principle. The forward reaction is exothermic, so a low temperature would give a higher yield of ammonia, but it would also make the reaction far too slow. So 450 degrees Celsius is a compromise, a lower yield but produced fast enough to be worthwhile. The forward reaction also has fewer gas molecules on the product side. 4 molecules become 2. So a high pressure pushes the equilibrium towards ammonia and increases the yield. The pressure is kept around 200 atmospheres rather than higher because building equipment to withstand even higher pressure would be too expensive and dangerous. The ion catalyst speeds up the reaction without affecting the yield. In the exam, explain both the yield and the rate-cost trade-off. Low temperature gives a higher yield, but it's too slow, so 450 degrees C is a compromise. High pressure gives a higher yield, but it's limited to about 200 atmospheres by cost and safety. The catalyst speeds things up, but does not change the position of equilibrium. NPK fertilisers. Plants need 3 main elements to grow well: nitrogen, phosphorus, and potassium. And NPK fertilisers are formulations that provide all 3. The nitrogen comes from ammonia, from the Haber process, which is used to make ammonium salts and nitric acid. Reacting ammonia with nitric acid makes ammonium nitrate, which is a great source of nitrogen. Potassium comes from potassium chloride and potassium sulfate, which are mined directly. Phosphorus comes from phosphate rock, but the rock itself is insoluble, so it's treated with acids to make soluble phosphate salts that plants can absorb, such as single and triple superphosphate. In the exam, remember NPK stands for the elements nitrogen, phosphorus, and potassium, and that an NPK fertilizer is a formulation containing all 3 in measured amounts. Phosphate rock must be treated with acid first because it's insoluble as it is.